Morning YouTubers. So, these 4 sockets were installed by me, my company, a couple of months ago to supply some kitchen equipment for a servery. This is the school kitchen. This is where they were serving. But the fireman who does the fire safety checks said the sockets have to be on the outside, so if there's a fire they can shut all the doors, because that's a fire door. All the shutters will come down automatically and the door is on a closer, so it should always be shut. So we've got 4 sockets to install here, which could be a challenge because we want to keep them as flush as possible, because otherwise kids stand on them and break them. And this is a twin plasterboard wall, so there's not much in the way of strength for putting surface mount sockets on, because a kid would just stand on it, break it. So we're going to get 4 single sockets there from there. So I've used my magic rod, little cheap rods, they're rigid, just to see where the studs are. So by taking the light switch out, I can see that the stud goes to there and the next stud is there. So is that 600? We say 600. 600 level. So we're just investigating how we're going to get there and keep that surface. So it's about 500 to the centre of the socket, providing the floor level is the same as next door. We should miss the pipes. So if we can put a pilot hole through and make sure it's not too obtrusive, from the rear of that socket we should be able to come around on the inside of the kitchen, around here and out through here somewhere. I think it's going to be our best route. A little bit grotty down here though, but in the name of keeping it nice, I think we'll put up with that. That will do nicely. Nice little hole there. I think we need to make it a little bit bigger. Magic. I think about there will do. This should do the job. Couple of holes, a couple of saddles for fixings, a little bit of conduit work around the back there to there, not fixed yet because I need to run the cables through and An alternative here is to use twin and earth because it's going into the void and be single insulated in the void, don't like that. So getting two twins through there to complete the ring, or extend the ring in this case, is going to be tight because of the bend. Not ideal, but it can be done nonetheless. One pair of 2.5 twin and earths installed in conduit. Wasn't too bad, a bit of French chalk helps. Ooh. So I've got all my cables in, just need to sleeve them, start putting double sockets on, single sockets. Obviously this is what we call in the UK ring circuit, so it goes from one to the next, to the next, to the next and back, giving you for example 32 amp on a 2.5 ring circuit with two 2.5 cables. There is a lot more maths that go into it, but if it was a single 2.5 you'd be looking at 20 amp. Yeah, I'm not going to do anything else about rings, but this is just how this circuit is and how we need to extend from it to keep the current capacity that's needed. Right, so we may have installed our new bit down to here, but we need to make sure it complies before we go any further. So, we need to test our new bit, test the old bit, join it together, test, lots of tests, compare it to the rule book, the electrician's bible in this country, and if it's safe and complies, then we'll connect it up and carry on. It did when we quoted for the job, so it shouldn't have changed, but you never know. Right, just going to do a little bit of testing now. Just do this for the camera. This is a loop test. This tests the resistance to this socket. There is some theory behind it. 0.57. We're looking for that number to be below a number in a chart, which I won't go into. And really we should find the furthest point on this circuit to make sure that that number complies, because the higher the resistance, the longer the device will take to operate, which could become dangerous if it's too high. So this is the low ohm resistance of the live and the earth going back from this point, oh look, that's not good, to the transformer and back again. So if you imagine this little live conductor in this socket goes to the fuse board, and then from the fuse board it goes back to the main fuse board, and then from the main fuse board it goes back to the transformer in the road, and the earth is the same. So the loop is the overall resistance of the copper cable from there to the transformer point in the road. Now we test the RCD that we've installed. And of course there's some maths and theory behind this as well, but all you have to know is that the RCD is there to protect you. And this will trip a number of times for this test. And the magic numbers we're looking for we'll see on the meter. Done. And of course, functional test. Sticker. And the results. 80 milliseconds, 1 times fault current, 30 milliamps, 0 degree sine wave, 28.2 at 180 degrees of the sine wave, 5 times fault current, 18 milliseconds, 0 degree of the sine wave, and 28.2 at 180 degrees of the sine wave. Brilliant. Looks like I need to get new batteries for the meter. That's good. I'll continue testing. Any questions on the theory of installing in our little country, UK, or any of the tests or any of the protection equipment like the MCBs and RCBOs, RCDs, that sort of thing. And if you live in a different country, let us know. I'll be interested to know what you got. Thanks for watching. And we went from that socket to there via a little extension. And that's what in the UK we call extending the ring circuit. Rings are quite interesting as well, so if you want to know about rings, let us know. I'll do a little video. Quite interesting. I don't usually get to film a lot of work because schools, cancer buildings, all that sort of thing, they get a little bit funny when you're recording when the little animals are in. But yeah, could have spent a little bit more time on this video, but I'm pretty busy. Oh come on, that went in that gap somehow.